Alright, hello guys. My name is Payton.
Hi, I'm Zhili.
And I'm Tianfeng Wang.
Our main project is to implement Fibonacci sequence using state mourner, so-called DoWith in our course. We will start with a naive implementation with the straightforward recursion according to the definition of the Fibonacci number. And secondly, we will show implementation using tail recursion. And finally, we will use DoWith to show you guys a cool implementation of Fibonacci sequence.
So quick recall of Fibonacci number. We know that the zeroth Fibonacci number is 0. And the first is 1, and the nth Fibonacci number is equal to the sum of n minus 1 Fibonacci number and n minus 2 Fibonacci number. There's a table showing the first 7th Fibonacci number. You can see here that the second Fibonacci number 1 is sum of the zeros and the ones. The fourth Fibonacci number is the sum of the second and the third.
The first part of our question is to implement the Fibonacci sequence using the recursion according to the definition. The function FibRec takes one argument n and would return the nth Fibonacci number. So you can see that we use the parting matching on n, and if n is 0, we return 0 directly, and if it's 1, we return 1. The case that we need to implement is the general case, since the nth Fibonacci number is equal to the sum of n minus 1's Fibonacci number and n minus 2 Fibonacci number. If we think indetectably, the answer is obvious. It's just FibRec n minus 1 plus FibRec n minus 2, since the FibRec function would give us the right answer.
This is actually a traditional example in algorithm class because this algorithm will be really time consuming and will result in a O2 to power n complexity. So we often implement that in another way. Since the nth Fibonacci number is the sum of n minus 1's Fibonacci number and the n minus 2's Fibonacci number, we can pass the value that we have just calculated to our new recursive call so that we don't calculate them twice during calculation.
To do this, we will use tail recursion. In the function FibRec tail, we write a Hilbert function called Fib, which takes 3 arguments a, b, and a and b are two accumulators which store the previous results. So for the base case, we should return a here. Actually, we could return b, but this would result in a different implementation for the general case. So we fix the base case to return a to maintain the answer for general case to be correct. It's not hard to implement. We update the parameters with the sum of a and b so that they keep checking of a new calculated result.
This would give us a linear time implementation, but there is a potential problem. If we calculate the Fib 15, we would use the result of Fib 10, but when we need the 10th Fibonacci number, we have to calculate that again. Why can't we store that if we use the number frequently? It would be really useful since it takes technically a one time to take that if we store that.
So I came up with the idea implementing that with DoWith, aka state mourner. First of all, let's quick recall on DoWith. DoGet will fetch the memory for us, and DoPut will change the memory and return us a new state and a unit here. So we somehow need to change the unit. DoReturn would not change the state and give us the state and the result. DoModify will modify the memory with a function. Pay attention that we still have a unit here, so we need to change that later. In this particular situation, we will use a new memory type, which is a mapping from integer to integer. Well, the first one stands for the index, and the second one is the nth Fibonacci number. So the memory will look like in this way. I also designed the do rules. The zero case is if we are calling for Fibonacci 0, we will return 0 directly. If we are calling with a parameter 1, we will return 1. If we want to fetch the Fibonacci number which is already in our memory, that will return that result directly. And if the value is not in the memory, we will calculate that and we give that a new mapping into the memory. So the result after running our function with parameter 5 would be this, and according to the do rule, the map should not include 0 and 1. For the code, the base case, of course, will be do return 0 or do return 1 according to the do rule. The general case is what we need to implement. So we call do get first to get the memory, and we try to get n from the memory. For those who are familiar with the language like C, this is actually like fetching the nth value from the array m. But it's actually a memory here, and this will return an option value. So there are two cases. The first case is a sum case. If we have sum case, which means the value is indeed in the memory, so we return that directly according to our do rule. And the none case is very interesting. It looks bad, but it's really easy to understand. So here are the code. So we call do fib on n-2, and we call do fib on n-1, and we modify the memory, and we give it a new mapping. It's changing the unit into the result. We call do fib n-2 here, and since we are thinking inductively, it will return the n-2 value, and do fib n-1 would give us the n-1's value. So the result here will be the nth Fibonacci number, and we modify the memory with do modify, so that will give us a new memory with mapping with a new mapping from n to the result. And finally, since this is returning us, it gives us a memory and a unit, so we have to change it. We use the map to fetch anything and change that into our result. That's it. So let's go to our code and see if it works. So this is the same code as in our slides, and we call this with do fib n, and we give this an empty map as its initial like memory. So you can see here, if we call this with 5, it will give us the mapping from 2, 3, 4, 5, and return the 5th Fibonacci number. Let's try 11. Yeah, and this will give us all the Fibonacci number from 2 to 11, and with the 11th Fibonacci number. And that's it. I'll post the code on Piazza with our slides and a video. And that's all for our main project. Thank you, guys.
Thank you.
Thank you.